Hello, I'm Hanjun Lee from ADAS Lab. Today I'm going to share dynamic planning for LLM-based graphical user interface automation, which is represented at EMNLP findings 2024. With the rise of LLMs, interest in LLM-based agents such as the multi-agents and research on GUI automation has grown. So thanks to multi-agent system, we can leverage the many features such as mobile GUI automation, desktop GUI automation, and so on. There are many helpful products on GUI automation, such as the OpenAI's operator, Cloud Computer Use, and Gemini Computer Use, which was very recently launched, and mobile GUI agents. So today I'm gonna deal with the mobile environment, the GUI agents. So GUI agents basically imitate the human's behavior. So given a user instruction, a GUI agent predicts and executes a sequence of actions that imitate humans' behavior. So these figures illustrates one good example when users say install WhatsApp on Play Store, then the GUI agents sequentially predict an action until finish the whole complete task. GUI agents framework composed of the several components: grounding, planning, and framework. Let me briefly share each component. Grounding in charge of the visual task using the OCR or VLM. So they basically compare between previous screenshot and the current screenshot to understand what was going on by the user's action and figure out what's the current state when given the user current screenshot and screenshot caption. Next, the planning part. On the planning parts, generally, they include the three agents: planning agent, decision agent, and reflection agents. So all of them are harmonized and making a plan and decide what action to do among all candidates. And after the executed the action, then reflection agent will check the previous action was wrong or did great. So if the action was the wrong, then reflection agent modify the previous step. Finally, the framework part. Framework part include the all components grounding and planning part, and also many helpful modules such as the database to control the memory, and also task list is one of the good example. In this case, task list help to manage the whole process. So it added the, the detailed context to the prompt, some things like that. So all of the components I mentioned are crucial, but the other end, I think planning play a crucial role in GUI task automation. Why? Current LLM, I believe that have the few knowledge about the GUI automation and the GUI understanding in mobile environments. So they shows a limited performance, especially because of the planning ability. They shows a little accuracy. So given a user whole instruction, the making whole plan is very crucial. Moreover, revising plan also crucial. As you can easily imagine that when you are using the mobile phone, the screen state changed very frequently, especially in the hidden spots. Internet connection was not good or any unexpected situation. Moreover, OS and application updated very frequently. As you can see, the Android OS updated annually, and one of your application updated almost daily. So the LLM, we cannot just stick to the previous knowledge, which is our supervised fine-tuning, pre-train, or reinforcement learning, whatever. The LLM need to revise based on the current state and the previous whole plan. So in this work, the author proposed DPOT, dynamic planning of thoughts, as an alternative to widely used React approach. So before we go to the main method, I just want to share the evolution of mobile assistance history. Bixby and Siri are the representative mobile AI assistants capable of handling usually simple or complex requests. They support tasks such as setting alarm, making phone calls, and information retrieval, and they have gradually evolved along with user convenience. Mobile Assistant has proceeded from API function calling to GUI agents to hybrid agents. As far as I know, currently most assistants are based on the API function calling, but I believe that in the future the GUI agents and hybrid agents will be the one key feature to solve the problems what I will mention on next slide. So in this part, I also want to share each simple briefing about the API, GUI, and hybrid-based approaches for each. The current mobile AI systems work based on the predefined APIs. So the biggest advantage of the API-based approach is high speed and strong performance. It's directly triggering the mobile functionalities. However, there are some limitations. It lacks flexibility for new applications or UI updates, and it shows a limited coverage of functionalities. Because I mentioned that their work based on the predefined APIs, so only supported the functionality has very limited. So these left figures illustrate one good example. The data, it consists of the query and corresponding API and parameters name. The right side of figures showing just one simple workflow in API-based approach. When you're asking something to AI assistant, then LLM will generate the whole intent. Then the mobile device will execute based on the generated intent. Next is the GUI-based agent. So the good part of a GUI-based approach is there is no dependency on specific APIs. In other words, there is no coverage constraints. So these figures illustrate a good example. So given a user instruction, the GUI agents imitate humans' behavior, so they just sequentially they interact with the current screenshot and they imitate humans' behavior. So you can easily imagine that there is no dependency on specific APIs. But however, there are also limitations, which is crucial, that they require many tokens and incur high latency. Because in every single step, model need to inferencing. So as a result, they shows a low success rate. Next is hybrid approach. So this method combines the strengths of both API and GUI-based approaches. There are pros and cons, but before we go to there, these figures showing the comparison between GUI-based agents and hybrid-based agents. So GUI-based agents, when users want dealing with some progress in Excel application, they need at least 5 steps to complete the task. But on hybrid approach, the model figure out that they can finish work with just one step using the API. So they can shorten the whole latency and reduce the total tokens, and they can show a better performance. So I just want I just want to emphasize again about the limitation that is they still suffers from low success rate, require many tokens and GUI high latency like GUI-based agent. GUI automation is long horizon task. So given user instruction and an initial screenshot, then the LLM agent explores the screen while managing progress toward the goal. So we must leverage the execution history and current progress to avoid redundant or unnecessary action, just leveraging the context and this framework with many tools. Also, the other insists that there are limitations of React in GUI automation tasks. React adopts a loop of environment observation to internal thoughts to actions. They records all past thoughts and action as input each time. So simply including more past dialogue history did not improve performance. So this table show and they compare the performance and in terms of performance and the cost between DPOT and React method. So as historic lengths improve, the accuracy gap is very limited. So even after the two turns appended, the accuracy is not improved anymore. And also it requires many tokens, which cause the total cost increase. In contrast, DPOT shows better performance with the limited, with very minimal the cost. So now let's move on to the method part. So the method part is very simple and direct. They just made a two-stage plan initialization and after dynamic plan adjustment. So before we go to the detail, let me share the input and output for each. So input is the current screenshot and goal, which is the usual instruction. And the screen caption is took from OCR or HTML DOM and execution history to see the previous whole history. Then output is a sequence of GUI actions predicted in JSON format. So as I mentioned that GUI agent basically imitate humans' behavior. So action type is described in the left side of table, click, scroll type, navigate, status, and press, which is very similar as humans' action. So right side of figures, just one example can show how can it work. They just defined with JSON format. So when LLM predict this action need to done by the click action, then the LLM will just generate the action type is the click, and you should click the UI components with IDX10. Very directional. So on plan initialization, there are two steps. So at the very first turn, the LLM generates the full action plan to reach the final goal based on the user instruction. It then identifies the current progress state and select next step with the highest executability. So this example shows a very simple example. Then when user instruction was given search news in the Google app, then the LLM will generate a whole plan, which is our go to home, click Google app, tap search bar, type news, enter, and done. And the given user screenshot is home screen, as you can see here. Then model will find out that because I'm now in home status, then I need to click the Google Apps. So after that, the LLM adjusts the whole plan at every time, which is very crucial. That, so after a step is executed, it is added to the execution history and update history is used in planning for next time. Thus, the agent continuously revises this plan to reflect recent action, entire past, and current state. So this is very crucial. So you might ask, revise the whole plan for every turn requires many tokens. Should it really work? Something like that. So I also worried at the beginning, but, but I mentioned before that they just define the action space with a JSON format. They require a less token. So even though they plan in every turn, uh, the limitation was not very far from here. So the history used very short expression to avoid increasing input length, the shorten inference time and improve performance they can show. So these figures illustrate one example that you can see. Just they stack up each history with JSON format. So now experiment and result section. So they just use Android in the wild dataset, which is widely used in mobile GUI automation research field. So this dataset consists of the usual instruction and each screenshot which represent the state. The other use backbone model for the other use GPT-4V model for backbone with the several the baseline, which is our zero shot, full few shot, react, reflection, and C-act. So DPOT shows overall performance gains over existing zero shot and reasoning baseline. So it consistently outperformed the baseline in most test categories. That suggests a generalizable advantage. And in some categories, in-store and web shopping, uh, they showed a limited the performance. So the other tests with human experts directly provided the plans. The success rate jumped from 23.6 point to 52.2 per 2 point, which highlighting the impact of plan quality. The author also tried to another experiment to alleviating planning hallucination and errors. To reduce planning hallucination and errors, LLM used reference similar task goal using sentence transformers. So they embedded each episode goal sentence and find top two similar episodes in the test set. So this retrieved information are appended to the prompt as a additional context. So this is represented on this table as a DPOT with reference. So they shows a 0.89% improvement, which is really great. In this part, the author also have the ablation study. So on this ablation study, the author defined four different type: MP, React, SP, and DP, which is our no planning, React, static planning, which is not the adjust the plan at every single step, and DP, dynamic planning, but the difference with the DPOT is on the DP state, they have no updated historical change. So on this table shows a many different evaluation study, and the other emphasize that both dynamic planning variants DP and DPOT outperform the others, confirming the importance of dynamic plan revision. So here, the author also tried another extra experiment. So they fine-tuned smaller model Llama 2 and Llama 7 Bilia for each under DPOT. So they were evaluated to check generalization skills to unseen tasks. So two training settings were used. So the other separate into the three segments. So segment one is they use as a baseline. So segment one trained with only 1% of samples in every category, and the other for segment two and three for each, they trained using data from the Google Apps category only. So one of the Android in the wild data set, and then they evaluate on other categories tasks to see the unseen task. So result was pretty good. So Llama 2 7 billion model shows that even training on single category, the performance was not far behind the original one. So I think one the limitation is they are powered by GPT-4V for planning part, which is not great, I think. And on segment 3, the Lava 7 billion model shows a model whose planning abilities enhanced via SFT can be more reliable than GPT-4V. As I mentioned the before slide, the Llama 2 7 billion model rely on the GPT-4V to make a comparable the performance. But in here, Lava 7B model, even just plan by itself, which means the planning by Lava model itself shows a better performance than GPT-4V and the baseline, which is really great. So, in summary, the fine-tuned smaller model under the DPOT also show that they can generalizable to unseen tasks as well. Limitation and future work. The limitations are there are practical issues. So directly learning on LLM-based agents on smartphones still faces many limitations, latency, resource constraints, something like that, and also domain knowledge issue. The agent's limited understanding of mobile domain makes it hard to achieve full performance. Future work is very clear. Broad improvements are needed in areas such as grounding, reasoning, and benchmark development. This approach requires multiple LLM inference. Reducing total task latency and cost is crucial. So this is end of my presentation. Thank you for listening my presentation.